Hello, my name is Julio. I work for SoundCloud in Germany, and I'm going to be talking about our continuous delivery strategy, more specifically about the specific practices that end up relying heavily on containers. So just in case you don't know anything about SoundCloud, SoundCloud is the largest audio repository on the internet. We provide services mostly for independent artists, individuals, organizations, podcast producers, and so on. And we operate at a fairly large scale at the moment. So we've been ingesting about 11 hours of content per minute. And we have about 300 million active users per month in our platform. Now, just to give a little bit of context about what I'm going to be talking here, I'm going to introduce a few basic ideas on continuous delivery, just in case you're not acquainted to what this actually means. So CD relates to the set of practices that allow changes to go to production with a specific set of characteristics. First, quickly, here meaning as soon as possible. In our reality at SoundCloud, we say we want it to be within minutes as opposed to hours or days or whatever. And safely, meaning we would like to make changes reaching the production environment with the highest level of confidence possible. Now, making this the approach to support quick changes to production is actually easy. So we could just go around and change files directly in the production servers and so on, and that would be quick. But it's not safe at all. Making it safe is what makes it hard. And safety is mostly derived from continuous integration. So continuous integration mandates that a change to a system is integrated in a mainline, meaning we are not dealing with long-lived branches or late integration. I know there is a little bit of a trend these days to use feature branches with pull requests on GitHub and so on. That potentially qualifies as continuous integration. Most of the time it doesn't. But anyways, don't want to be controversial on this specific topic. What we prefer is to say we develop on a mainline, every single change is always merged and tested. Now, continuous delivery is fundamentally continuous integration with the last mile aspects covered, meaning we like to be testing the deployment to the production environment continuously as well. Now, there is a lot to do, a lot of topics related to this, to continuous delivery, continuous integration, continuous delivery that I could be talking about here, but not every single thing will be interesting in this specific context of talking about containers and how these things can be used. So I'll limit it to a specific set of goals that we found containers to be extremely beneficial for. So to start with, let's talk about isolated test integrated environments. So what do I mean by that? Well, to start, let's talk about our history and how we got to the current architecture. So just when the company started, we were like a fairly small startup, like 7 years ago. We have a small startup, few developers. They were experimenting a lot. And what they built was this one single monolithic code base, which they called the mothership. And this worked fairly well for the first couple years of the company. So developers could go around and make changes, and cycle times wouldn't be too long. So they had a lot of contact with independent artists and producers. So we got a lot of traction out of this one single Rails application. Now, the problem was that eventually this didn't work anymore. So as we started having more and more developers, well, eventually continuous integration broke. So what could potentially be solved by adding more testing infrastructure to support the development on the monolithic code base ended up being a major re-architecture of the system. So at that stage, we decided to say, let's shrink down the functionality in the mothership. Let's do a smaller code base there and start migrating this into a bunch of smaller, a huge amount of smaller microservices. And we ended up building a huge amount of them. At this stage, we have hundreds of microservices. The functionality of Mothership, and Mothership still exists, by the way, even after many, many years developing this thing, developing code to move functionality away from it. We still have it. But the deal with microservices is that, well, eventually it started becoming a problem as well. So what could go wrong with this kind of architecture? So the pattern that keeps repeating itself seems to be that when you start developing a system, and you don't have to do with a lot of integration points, the cycle times, the amount of time that it takes for you to make a change and know that it works, and consequently deploy to production, is usually short. So there's not that much of an integration point there. It's usually a little database, perhaps a couple RESTful endpoints that you have to talk to. Those are easy to stub or just develop against proper integration, proper deployments. But things go well. As more integration points are added, things get really ugly. And they get really ugly very fast. So what we found is that by the time that we get 20, 30 of these microservices, these cycle times were excessively long. And why this happens, and by the way, this is a full circle. We kind of got to the same situation with Mothership, with the monolithic code base as well. But then why you didn't do anything about the original code base? And we started doing this thing. This way is that when the system starts, developers are extremely confident that things are going to go well. They say, well, we're doing something that is positive. We're not facing the old problems anymore. And they are mostly not facing because they're not dealing with integration problems still. But as things go by, and also why they start breaking functionality down, there is not that much of a pressure from the business side to add lots of functionality. So the business is sold on the idea. They want they like the idea that developers are now quick. They start planning new functionality on the system on the basis of the performance of the teams in that state where they don't have to do with a lot of integration. And when these systems start becoming mature and they start adding more integration points, that's when things get really ugly. Now the business wants more. Developers didn't put a lot of infrastructure on this, and this infrastructure is usually very hard to build. And all sorts of nasty practices kick in. So you see here developers building testing that takes forever to run. They can't run in their local machines, so they depend on server-side testing, like they use the CI server to run the tests for them. The thing is always broken, and then they don't rely on the tests anymore, and then, well, it becomes a mess. So there has to be some force here to stop this process from happening. And well, let's reason about that, and let's get to the point where we actually have a proper solution for this. So we can think of the workflow for development in just 3 basic stages, so let's call them a pipeline. So we have a build, test, and deploy pipeline. So usually when you build, you would like to be building a binary artifact that you're going to be testing later in an integrated environment. So the same binary that you built originally, you use it in a testing environment, and the dependencies that you built that you're using for the testing environment come from previous builds from the other applications that you depend on. And that same binary goes to production environment. So no such thing as let's build the application once, and then we build it again for testing, then we build it again for deployment, or we deploy based on source code or anything like this. We would like to have some safety out of building a binary that once it's built, it's tested and goes to production. This is fundamental. But when it goes to safety, the key part of this conversation becomes the integrated environment. So we sort this problem, we kind of enable developers and consequently the company to be quick. So how do we go about that? I think that there are 2 traditional ways of building integrated environments that enable teams to be quick. One of them is to build stubs. When I mean stubs here, I don't mean re-implementing at the code level a service that would like fake the original system. I mean building an actual literal server that would have the same behavior as the original system. So for instance, you have a RESTful service somewhere, and you want to stub it, what you build is another HTTP server that is only capable of responding to test data. Now, these things can be built in many ways. You can handcraft data, testing data directly in code, or you can do record replay strategies, whatever they are. And the matter is that they actually work fairly well. In fact, it's one of the most, it's one of the quickest, it's one of the approaches that allow for building test environments that are the quickest. Things extremely, the stubs tend to be fairly efficient. They have low footprint, they boot very quickly. So they make sense, except that they demand a lot of development effort. So you have to go around, craft this stuff, and make sure that they are always in sync with the actual systems that are going to be integrating against later. Now, from a few other projects that I worked in the past, we had to do with a lot of integration. I measured the amount of time that it takes to build these stubs. When I mean integration, it's counted on the dozens of other systems that a given system will have to integrate against. The amount of time that it takes to build stubs and maintain them so that they will be quick and reliable is considerable. It's in the range of 30% of all development efforts for a team. So in the SoundCloud reality, we thought, well, perhaps that's not going to work very well. As a matter of fact, we were using a lot of stubs. They worked, but then again, they were demanding a lot of effort. So we said, let's not do stubs. Let's try something else. Let's try to build the actual services in local machines. These days, we have fairly powerful laptops. What if we could deploy the real systems that we use in production in an integrated environment locally? So for that, we started running, we started crafting containers, Docker containers. So we built Docker files and all that stuff manually for chunks of the architecture to make sure that we could actually deploy a reasonable, realistic part of the ecosystem in a local machine and run tests against it. And it worked fairly well. For the kind of stuff that we do, it worked fairly well. Now, I'd like to mention that we have everything under the sun in terms of technology these days. So we still have a lot of Rails-based stuff. We have a lot of Java, Scala, I mean Java as in Java itself, Scala, Clojure. Then we have Python, Erlang. We have everything under the sun there. So it's not that we can just say it's just Java and therefore the problem is easy to solve. So we can deploy everything in a single JVM potentially even. Some folks out there are doing these things, but we can't really afford that. So containers are actually a fairly, it's a viable and very interesting solution for us. So at that stage, we established that it would make a huge amount of sense to start building Docker containers specifically to support the building of test environments. All right, so pause this conversation for a second. Let's talk about some other problem that we had that was happening at the same time that we were doing the microservices. So we were breaking down the architecture, but we were also building our, like 5 years perhaps ago, we were also building our own container runtimes or schedulers and so on. So it's like based on the Heroku model. So you specify a SHA from the source code, and it deploys from there. It builds an image, and then it deploys from there. Now, it made a huge amount of sense for us. I mean, I know that many other folks out there in the industry did the same thing with varied results. For us, it worked fairly well. But by last year, it didn't make sense anymore to maintain this thing because things like Mesos, Marathon, Kubernetes started appearing, and they were becoming fairly stable. So we said, well, let's not do this anymore. Let's migrate into something else. And then we did trials to see what would make more sense for our style of deployments. And then we selected Kubernetes for a few reasons. One of them because we wanted to make deployments on active and active style. So we'd keep the systems running in production, then deploy another cluster and warm it up and then switch traffic. The primitives in Kubernetes would allow us to do that. We also like the idea of doing deployments on pods. They're isolated, namespaces are isolated, and then we could do monitoring, logging, alerting, everything in isolation from other applications. And that's what we do these days, by the way. So it made a huge amount of sense. And potentially, even Kubernetes would help us building local deployment, developing environments. So I could just deploy a little Kubernetes cluster locally for that. something we're exploring. Still haven't deployed anything like this yet. So it makes a lot of sense to do that. Now, immediately we have a problem when we make this decision, because our current runtime has its own image format. So we have to build a tarball that is an image for this thing. And if we're saying we want to move to Kubernetes, now we have to build Docker images as well. And we would like to be building these things in a way that is consistent, meaning we don't want to come around and say, yeah, the system is working on the old system, the old platform, and if we switch to Kubernetes, well, it has a different way of working. We want it to be fairly consistent. And also, we don't want it to be a big bang migration. We want it to be system by system kind of thing, from lower risk to higher risk, so that we can evaluate the platform as we go. That's what we're doing. But then, again, we already established that we wanted Docker for integration environments. And here we say we need Docker for building Kubernetes pods. But we still have to maintain the old system. So how do we go about that? Now, what we decided was to say, well, we already had a lot of trouble with the lock-ins that we have with our current platform. We don't want to get into the situation where we do a full circle again. So we want to build artifacts here in a way that doesn't incur into a lock-in. So we don't want to be locked into Docker. We don't want to be locked into Kubernetes in the same way that we don't want to be locked into our current platform. So let's select to build the containers based on Debian packages. So we provide the tooling for the developers so that they can build the Debian package folder structure from their build systems. So if they're using Scala, we provide an SBT plugin that builds the folder structure that we want, which is standardized. If they're using, Rake, then we provide a Rake plugin, and so on and so forth. And from here, we build a Debian package. And this is standardized. And all the dependencies that a given application has, including its runtime, are specified at a Debian package level. Now, from the Debian package, then we derive the images. So then we derive our proprietary format, and we derive Docker. Now, this allows us to say we don't have any lock-ins anymore. So if at some point we say we don't want to use Docker, or we want to use Docker and Rocket at the same time, or we want to start building unikernels, whatever, we have full flexibility for that. As a matter of fact, if we don't even want to use Debian in the future, we can switch away from it. The original structure that we built for building the Debian package is actually fairly not Debian specific. So, and we have full control over that from the plugin side. So this is all centralized, meaning that by just using this, now we're completely independent from the actual runtime that we're going to be using. And to be fairly honest, even if we didn't have the original proprietary stuff, we would still do it, just because we don't want to have the lock-in problem there. Okay, so let's pause this again. Let's talk about the goals. So we established that we want Docker for the integration environments. And we said we want also Docker to run on Kubernetes, but we don't want it we don't want to be locked into Docker. So we go around and build images from a binary source of truth, which is a Debian package, which could be, by the way, anything. It could be RPMs or anything. We just selected Debian because that's what we already use in production anyway. So what's the next little problem here that containers came around to solve a major problem for us? It's about build environment consistency. Well, what we see more frequently than not is that whenever people talk about containers and running stuff in production, yeah, they say we have automation that actually builds an application, and then using Docker, or we run a Docker file, and then it builds an image, and then we can run this stuff. But in practice, what we observe is that in order to build an application, you need, for instance, for building a Java application, you need a runtime to you need a JDK, or you need a development kit in order to compile and build the application. plus a few development tools, which can be things as simple as make and git, but in some cases it may be more complex. In order to run the application, you need a JDK. And then the same thing is going to happen in the CI infrastructure. So there you also need a JDK for building, you need to build dependencies, and you need a JDK to run the application. And when it goes to production environment, you need another runtime. And unfortunately, these things tend to be inconsistent. So whatever is running in the developer machine may be different from what is running in the CI server, may be different from what's running in production. For the specific case of JDK, that's not so much of an issue, but it is an issue for things like Ruby and Python, Erlang, and others. So our solution for this is to say the same thing, the same practice that we apply to build the applications in terms of building a Debian package and then deriving the containers, we use for the runtimes. So we build a Debian package for the JDKs, we repackage a JDK or Ruby or Python or whatever. And from that, we derive the other containers, and from the Docker images specifically, we create a Docker image with the development dependencies, which means that in order to build an application, really all you need is Docker. At this stage, if at some point we want to move away from Docker, that's fine, we can still support it. But Docker is sufficient to build any application, and the build that runs in a local machine is precisely the same that runs in the CI server. Also, because we do this, the CI infrastructure doesn't have to be specialized anymore. So in the past, we had specific agents or slaves, CI agents or slaves, that were specialized to build specific stacks. Now we don't need that anymore. So we can build slaves that are elastic, so they scale on demand for the whole of the organization. And all they have to do is to run Docker. So here's an example. We have JDK, then we build our format, like we build our tarball that is used for our current environment. And then for Docker, we build in our namespace a JDK8, and then we derive a JDK8 dev. Now, just going for the mechanics on how this works, an application that depends on Java, depends on JDK8, for instance, would declare that dependency at the Debian package level only. When we build the Docker image, we build the Docker image to extend the layer that already has the JDK installed, so that whenever a developer or a CI build, for that matter, runs the build, it already most likely have the layer downloaded in the machine. So all it has to do is to install the application itself. So this is a fairly optimized model, and for distribution as well. When it goes to distributing the application, because of the layering in Docker, we don't have to redistribute the runtime everywhere. So in practice, we only redistribute the application changes themselves. And here's just a snapshot of a bunch of the runtimes that we built. And we take them as, again, build, test, deploy kind of stuff. We do deployments here. I'm going to talk about deployments later, but we do deployments that are consistent across all the runtimes at the same time. So it's not that we can do a change to JDK and make sure that, and know that everything's going to work in production. We have to change all the tool set at once and then do kind of monolithic deployments to production to guarantee that we are not going to be breaking everything for the developers. Okay, so one last problem here that, again, is usually overlooked when we're talking about containers and how to bring stuff to production, that is related to versioning. So then again, referring to the generic pipeline that we have here, when we build the application, that's when we build an artifact, and we claim that it's tagged as testing, which means it's not known if the thing is working or not. Nobody should be integrating with this state of the artifact. Once we test it, then we claim that it's stable. Therefore, it could be integrated against. It's ready to go to production, but it's not in production yet. Once it goes to production, we call it release. So the terminology here is we publish the application, the artifact once in the first stage, and then we promote it afterwards in the subsequent stages. Now this tagging, well, there is a version associated to each one of these tags. So there is a complex version that is based on the GitHub, the build number of commits to the repository, and so on. There's a unique tuple that classifies each one of the artifacts. But these tags have to be consistent across all the repositories. So if you're saying we are using Debian, then these tags have to be consistent in between the apt repo. If you're using Docker, they have to be consistent in the Docker repo. And we build metadata out of this. Let me talk about the metadata problem here. So in the testing stage, we say we have to create an integrated environment. So here we are testing one system across with a set of all its dependencies. Now, which versions of the other dependencies should we be using here? We say we can either integrate against the stable versions, which are the versions that are potentially not deployed to production, or the release ones, which are the ones in production. For the most part, we integrate against the versions that are in production. So here I'm going to be testing my system against all the other versions that are already deployed. Now, I have to know which versions are those, and then what we do is we record those versions in a manifest. So here's an example. So for this system called API Mobile, I just copied a few of the dependencies that it has there. But then there is authenticator, and that's the version that it's testing against at this point. Which means that by the end of this pipeline, if this pipeline is green, so if it works, if testing here works, the integrated environment that was built for this version of this system, API Mobile, is known to work against those versions of the other systems. It's not guaranteed to work against any others. So this thing says that these ones are good, and those are the safe ones. We could go to production if those versions are still in production. But that's very unlikely to be the case. So if we allow each one of these systems to deploy directly to the production environment, most likely what's going to happen is that each system tests itself against specific versions in production environment. But by the time that it gets deployed, some system may have changed its version. So then we have an inconsistency. There are many ways to solve this problem. But the way we decided to resolve it was by building a downstream, fully integrated build. So this means these builds don't actually create in a binary artifact. All they do is to run the tests for all those systems together. It runs a few end-to-end tests for all these systems. And the versions the manifest for the versions that it builds here, that's good stuff, because those are the ones that we can always deploy to production. It's just that we don't deploy systems individually. We deploy the deltas. So if here we calculate a set of versions that are known to work together, once we go to the production environment, we say, all right, what is the difference between the versions that are in production with the versions that we just tested? Whichever systems change versions, we deploy together. And because now we are using Kubernetes, we can do active-inactive. So we're deploying these versions to inactive environments, warming them up. We can run a few canary tests there to make sure that everything is fine, and then we switch traffic. If anything goes wrong, we can always either do a very quick rollback on the older active environments, which are now inactive, or we can rerun this pipeline for an older version. So we can do rollbacks by just redeploying. And in either case, we can always reason what actually happened, because you can see the set of versions that existed in the integration pipeline, in the main pipeline, with the versions that happen in each one of the individual pipelines, and see what gives. Why is that something went wrong in the production environment? So by doing so, now we can add more regression to the testing and guarantee that this potential problem is not going to happen again. Now, this may sound counterintuitive that we're actually building a downstream thing here in order to optimize for speed, because now we have a contention on a single pipeline that is going to be running for every single system. But the fact is, we don't really have to have a single one for the whole of the organization. In our architecture, we can find that there are clusters of systems that are tightly coupled, but there are many clusters that have very weak coupling between them. So think of, there is a process that does ingestion of content from third parties. There is a process that serves content to the end users. Those processes are, the coupling there is fairly small, and it goes through S3 on Amazon. So the risk that we're going to be introducing a change on one system and break integration on another one is fairly small. So then we make a trade-off there and say, we split the architecture into heavily coupled groups or clusters, and for those we build integration pipelines. So we don't have to have a single one for the whole of the organization. Now, so just as a recap, we established that we wanted integration environments, so Docker made a lot of sense, and it's extremely beneficial for us. So using Docker Compose and our own in-house strategy to deploy these environments. In order to support migration to another production runtime, we use Debian packages, and then we derive containers from that. And because, again, we're using Kubernetes, we're benefiting a lot from what Docker provides to us. We build environment consistency by creating containers for building the applications, not only to run the applications. We use containers heavily to build everything. And we deal with the versioning problem by creating pipelines that run integration tests for the whole of the organization, for clusters that compose like a good chunk of the architecture. And with that, I'd like to thank you guys. I think we have a little bit of time potentially for a question or two if you want. But that's it. Thank you so much.
So you have a very nice-looking website, which means presumably you have product management and design people who are very interested in this whole loop, making sure that things look and feel good. And these are very hard to test for. Can you spend a moment talking about where like a human being in that pipeline might have a go, no-go? Does it happen at the end? Does it happen at the beginning?
So this goes into the structure that we use for the teams. So teams have product owners, and each team has a designer component to it. So there are designers working directly with the teams. I think we do a lot of experimentation. We do A/B testing and everything with the users. So for some chunks of users, we actually deploy different versions of the website to validate if things are working better for them or not. But the thing is, in order to enable those processes of changing things quickly, we need to enable the teams to be fairly quick in changing something, get it to production. If things go well, it sticks. If it doesn't go well, we can change it very fast later. I'm not sure that this is the answer for you, but as far as we're concerned, this is an enabler. So what we're trying to do is to allow them to be very quick. So in speed for us will enable teams to bring as many changes as they want to the production environment and test for any changes in the UI.
Okay. Unfortunately, we're over time right now, by about 5 minutes, so we need to.
Yeah, we can catch up later if you want. All right. Thank you, guys.